Welcome to the week 7 of SWAYAM course on Introduction to Electric Vehicles and Hybrid Electric Vehicles. I am Dr. Venu Sonti, Assistant Professor in Department of Electrical Engineering, National Institute of Technology, Raipur. Last week, we explored the concepts of induction machines. We have seen the speed control techniques of induction machine along with the vector control technique. In this week, we will focus on the permanent magnet synchronous machines which are used in the electric vehicles. We will delve into their construction, working and vector control of permanent magnet synchronous motor. By the end of this week, you will have a comprehensive understanding on how permanent magnet synchronous motors are utilized to optimize the performance and efficiency of EVs. Permanent magnet synchronous motors do not consume electrical energy for field excitation, eliminating the excitation losses and significantly boosting the efficiency. Using permanent magnets allows for higher torque and power output unit volume compared to the electromagnetic excitation. Permanent magnet motors offer superior dynamic performance with increased magnetic flux density in the air gap compared to the magnets with electromagnetic excitation. The construction and maintenance of permanent magnet based machines are simpler. Cost can be reduced for certain types of machines using the permanent magnets. The materials used for construction of permanent magnets should possess the properties like high flux density and high correctivity. The rare earth magnetic materials are ideal for meeting these criteria. For instance, samarium cobalt is widely used material due to its high flux density which can reach up to 1 Tesla and is substantial corrosive force which has almost equal to 7000 ampere per centimeters. Currently, neodymium, iron, boron magnets are popular due to their cost effectiveness. Additionally, these magnets are space efficient and with careful design they are resistant to accidental demagnetization even during a short circuit. Now, if you see the BH curve of this permanent magnet, here the diagrams highlight the magnetic properties of material used in the permanent magnets. Neodymium, iron, boron and samarium cobalt show high flux density up to 1 T or 1 T and high corrosivity making them resistant to demagnetization. Alnico and ferrite have lower flux density and corrosivity making them less suitable for high performance applications. The BH curve illustrates how permanent magnets behave under different loads. High corrosivity ensures that magnet resists demagnetization even under full load, maintaining stable motor performance. Next, coming to the construction of permanent magnet synchronous motors. Like other motors, here also we have the stator and rotor. Now, coming to the stator of permanent magnet synchronous motor, the stator is connected to the supply. This stator is made up of laminated iron core with winding. It typically uses a 3-phase winding to produce a rotatory magnetic field. The stator windings are placed in the slots on the inner surface of the stator. Next, coming to the rotor. The rotor is the rotating part of motor and is placed inside the stator. It contains permanent magnets made up of materials like neodymium, iron, boron and samarium cobalt. These magnets are either embedded within the rotor or surface mounted. The design of rotor ensures it provides a strong and consistent magnetic field. The use of permanent magnet eliminates the need for electrical energy to create a magnetic field, resulting in higher efficiency and improved performance. Next, if you see the construction of permanent magnet synchronous motor, to understand this construction, let us consider a 4-pole synchronous motor. This motor have solid steel rotor with samarium cobalt magnets attached to it using standard bars. Now, in many applications, especially in the servo systems, achieving smooth and precision torque control is a crucial aspect. Here, one of the challenges that we face in this system is minimizing the cogging torque. The cogging torque is an unwanted ripple in the torque output that occur because of interaction between the rotor magnets and stator slots. This can lead to uneven motion, which is not ideal for applications that require smooth and controlled movements. Now, coming to the projecting type permanent magnet synchronous motors, here the mounting motors on the rotor surface is simplest and cost effective method for constructing this PMSM type. The epoxy glue is commonly used to secure the magnets to the rotor surfaces in both projecting and inset surface mounted permanent magnet synchronous motor. Despite its simplicity, this construction is less robust compared to the interior magnet type rotors and is not suitable for high speed applications. The relative permeability of magnet is nearly equal to that of air, allowing the projecting surface mounted motor to maintain almost uniform air gap. This uniformity results in equal direct and quadrature axis inductances. The motor torque is derived solely from the magnetic flux without any contribution from the reluctance torque, which is typically seen in the salient magnet construction. The projecting magnets create a large air gap in the magnetic circuit, which reduces the machine's inductance. The lower inductance leads to a smaller stator time constant. The surface mounted design often results in smaller rotor diameters with low inertia. This design enables the machines to exhibit good dynamic performance. This type is used in making drives suitable for high performance applications, including machine tool feed drives and industrial robots. Next, coming to the insert type permanent magnet synchronous motors. The insert permanent magnet synchronous motors have magnets that span less than a pole pitch mounted into the rotor surface with an iron rotor tooth filling the space between the magnets. This design makes the machine mechanically more robust and increases the inductance compared to the projecting surface mounted PMSMs. The quadrature inductance is larger than the direct inductance because the magnet is equal to an air gap in the direct axis. This saliency in the design introduces a significant reluctance torque, which adds to the magnetic torque. Next, coming to the interior type. The interior type PMSM is an alternate to the surface mounted designs having magnet embedded within the rotor's interior. The interior magnet design offers mechanical robustness and a smaller air gap compared to the surface mounted permanent magnet synchronous motors. The reluctance torque obtained in the permanent magnet synchronous motors is much higher than that in the inset magnet motor types. Next, coming to the working principle of the permanent magnet synchronous motor. In a permanent magnet synchronous motor, the rotor is equipped with permanent magnets that generate a constant magnetic field. Unlike traditional synchronous generators, where an electromagnet is used, the permanent magnets in the rotor of PMSM eliminate the need for separate field excitation, making the design more efficient and compact. This constant magnetic field in rotor interacts with the magnetic field produced by the stator. The stator contains three-phase windings that is supplied with an AC current. This current generates a rotating magnetic field in the stator. The key to efficient operation in permanent magnet synchronous machine is to keep the angle between the magnetic fields of stator and rotor close to 90 degrees, which maximizes the torque output. As the stator's magnetic field rotates, it pulls the rotor into synchronous speed, meaning that rotor rotates at the same speed as the stator magnetic field. This synchronism is maintained because the frequency of AC supply to the stator is adjusted to match the rotor speed. The rotor position sensor plays a crucial role in this process by monitoring the rotor speed and position, ensuring the synchronism is maintained even when there are changes in the load torque or frequency. One of the key advantages of permanent magnet synchronous motors over induction motors is elimination of slip. As there is no slip, the rotor magnetic field is constant and does not rely on induced currents. This leads to precise synchronization between rotor and stator fields, ensuring high efficiency and consistent operation. Furthermore, the rotor magnets acts as a source of magnetic motive force, which reduces the synchronous reactance and minimizes the effects of armature reaction. This design features contributes to high efficiency and excellent performance characteristics, particularly in applications requiring precise speed control. Next, coming to the modeling of permanent magnet synchronous motor. The DQ analysis of permanent magnet synchronous machine is done specifically focusing on non-salient type poles where the rotor can be considered magnetically round. The analysis is important for understanding how to control these machines effectively in various applications. The rotor has surface mounted permanent magnets and is magnetically round, meaning the reluctance is same along any axis through the center. The stator windings are 3-phase and sinusoidally distributed windings in space, similar to an induction machine. These windings are denoted by the terms IA, IB and IC, each aligned with the A axis, B axis and C axis. In the figure, you can see here the DQ analysis of permanent magnet synchronous machine. Here, D axis is always aligned with the rotor magnetic axis and Q axis is 90 degrees ahead in the direction of rotation, assumed to be counterclockwise. The stator winding are transformed into equivalent D axis and Q axis winding, each with 3/2 ns turns, where ns is number of turns per phase. This transformation simplifies the analysis by focusing on 2 orthogonal axes instead of 3. The flux linkage is a measure of magnetic flux linked with coil or winding. In permanent magnet synchronous machines, it represents how the magnetic field interacts with the stator windings. In the context of DQ analysis, the flux linkages are divided into components aligned with D axis and Q axis. The flux lambda SD is equal to Ls ISD plus lambda FT and the flux lambda SQ equal to Ls ISQ, where lambda SD represents the total flux linkage in stator D axis winding. The D axis is aligned with the rotor magnetic axis, meaning that any magnetic field generated by the rotor directly contributes to this flux linkage. Lambda SQ represents the total flux linkage in the stator Q axis winding. The Q axis is perpendicular to the D axis and does not directly align with rotor magnetic field. ISD and ISQ are the current flowing through the stator D axis and Q axis windings. Lambda FD is the flux linkage due to rotor permanent magnets. Since the D axis is always aligned with the rotor magnetic axis, lambda FD captures the contribution of rotor's magnetic field to the total flux linkage in the D axis winding. Here, lambda FQ term is not there in the equation. This is because rotor's magnetic field does not directly influence the Q axis flux linkage as it is aligned with the D axis. The equations for flux linkages in DQ reference frame simplify the analysis by breaking down the magnetic interactions into the components along orthogonal axis. The D axis flux linkage includes the contributions from both stator currents and rotor magnets, while Q axis linkage is only influenced by the stator current. The stator voltage equations describe how the voltages applied to the stator winding relates to flux linkages, currents and rotational dynamics of the machine. In DQ reference frame, these equations take into account not only the direct effects of stator currents, but also interaction between the D and Q axis due to rotor's motion. The stator DQ winding voltage equations combine resistive effects, dynamic flux linkages and rotational coupling to describe the complete electrical behavior of permanent magnet synchronous motor. These equations are foundation for designing control strategies that ensure efficient and stable operation of the machine. The stator DQ winding voltages are denoted by the terms VSD and VSQ. Here VSD is equal to RS ISD plus d by dt lambda ST minus omega m lambda SQ. Next, VSQ equal to RS ISQ plus d lambda SQ by dt plus omega m into lambda ST. Here RS ISD and RS ISQ represents the resistive voltage drop in D axis stator winding, where RS is the stator resistance. Next, omega m lambda SQ and omega m lambda ST introduce the coupling between the D axis and Q axis due to rotor rotation. Omega m is the mechanical angular velocity of rotor. The coupling terms omega m lambda SQ and omega m lambda ST highlight the importance of the rotor's motion when analyzing the machine's behavior in DQ frame. In order to keep the D axis aligned with rotor magnetic axis, the speed of equivalent DQ winding is omega d, that equal to omega m. The speed omega m is related to actual rotor speed omega mechanical as omega m equal to p by 2 into omega mechanical. On the rotor D axis winding, the torque produced is due to the flux density produced by the Q axis winding. Td equal to p by 2 into lambda QR into IRD. On the rotor Q axis, the torque produced is due to the flux density produced by the D axis winding. TQ rotor equal to minus p by 2 into lambda RD into IQR. Here lambda RQ equal to Lm ISQ plus Lr IRQ and lambda RD equal to Lm ISD plus Lr IRD. By superposition, adding the torque acting on the D axis and Q axis of the rotor winding, the instantaneous torque is equal to sum of the TD rotor plus TQ rotor. So, from this the torque TEM equal to p by 2 into lambda SD ISQ minus lambda SQ into ISD. Here substituting this flux linkages for permanent magnet, the electromagnetic torque can be expressed in terms of inductance. The torque TEM equal to p by 2 Ls ISD plus lambda FD ISQ minus Ls ISQ ISD. So, this is equal to p by 2 into lambda FD ISQ. Next, if you see the relation between the DQ circuits and per phase phasor dominant equivalent circuit in balanced sinusoidal supply. In this section, we will explore how the DQ axis equivalents relate to their per phase equivalent circuit of synchronous machines under balanced sinusoidal steady state conditions. Understanding this relationship is crucial for analyzing and designing the synchronous machines, especially in applications like permanent magnet synchronous motor drives. Under balanced conditions, the TQ axis components becomes constant, nothing but the DC quantities. The time derivatives of this DC quantities becomes 0, simplifying the analysis. For synchronous motors in permanent magnet synchronous drive, the synchronous speed omega synchronous is equal to the rotor speed omega m at all the times. Substituting this flux linkages, the stator voltage equation VSD equal to RS ISD minus omega m Ls ISQ and VSQ equal to RS ISQ plus omega m Ls ISD plus omega m lambda FD. To change the DQ representation to per phase equivalent circuit, we combine the effects of both DQ circuits. This is done by manipulating the stator voltage equation in DQ frame to form a space vector which can be interpreted in the phasor domain. Next, coming to the space vector approach, Vs is equal to RSIS plus j omega m LSIS plus j root 3 by 2 omega m lambda FD. By converting the space vector equation into per phase domain, we can derive a phasor equation that corresponds to each phase of synchronous machine. The result is an equivalent circuit that matches the classical per phase representation, making it easier to analyze the machine's behavior under steady state condition. The voltage Vs is given by Vs equal to root 3 by 2 Vsd plus jVsq. Dividing both sides of above space vector equation by 3 by 2, we obtain the following phase equation for phase A in the balanced sinusoidal steady state condition. Va equal to Rs Ia plus j omega m Ls Ia plus j omega m root 2 by 3 lambda Fd. This is the per phase equivalent circuit in the steady state. Here the equation shows the relationship between the back EMF of motor EFA and the flux linkage lambda Fd due to the field winding and the mechanical speed omega m. EFA equal to root over 2 by 3 into lambda Fd into omega m. Here this term root over 2 by 3 into lambda Fd is denoted by a constant Ke, which is nothing but the voltage constant of motor. Next, coming to the speed torque characteristics of permanent magnet synchronous motor. The speed torque characteristics of permanent magnet synchronous machine are shown here. For a given Ke, the maximum permissible voltage and current, the maximum torque remains constant from a low frequency to F0. At F equal to F0 and F equal to F max, the torque developed is 0. The shaded portion represents the permissible region of operation in the speed torque characteristics. In the speed torque characteristics, if speed is increased beyond the point D, there is a risk of overcurrent because of the back EMF, increase in the back EMF while terminal voltage remains constant. The current is then almost pure reactive current flowing from the motor back to the supply. There is a small Q axis current and small torque because of losses in the motor and the converter. This mode of operation is possible only if motor overspeeds the converter or is driven by an external load or prime mover. Next, coming to the vector control of permanent magnet synchronous machine. The permanent magnet synchronous machines widely used in applications that demand high efficiency and precise control. Unlike simpler control methods, vector control allows us to achieve independent control of torque and flux, which is crucial for dynamic performance. The first key concept here is transformation from three-phase currents IA, IB, IC into two-axis system called DQ coordinate system. This transformation simplifies our control by converting the AC currents into DC currents in the rotating reference frame aligned with rotor's magnetic field. The D axis aligns with the rotor flux and Q axis is perpendicular, allowing us to control the torque and flux independently. Next, we have the reference currents ISD dash and ISQ dash that represent the desired values. These are compared with actual currents ISD and ISQ, and the error is fed into PI controllers. The PI controllers then adjust the voltage command VSD reference and VSQ reference to minimize this error, ensuring that the motor operates as desired. The coupling terms compensate for interaction between the D axis and Q axis currents due to the motor's inductance and speed. Once we have determined the correct DQ voltages VSD dash and VSQ dash, we need to transform them back into the three-phase AC voltages VA star, VB star and VC stars using inverse spark transformation. These voltages are then used to generate PWM signals that control the inverter, which in turn drives the motor. Accurate control requires knowing the rotor position, which is provided by a position sensor. The rotor angle theta m is crucial for aligning the D axis with rotor flux during DQ transformation. The motor speeds omega m from this feedback position, which we use in our decoupling terms. Now let us explore some advanced vector control techniques that take permanent magnet synchronous motors to the next level in terms of efficiency and performance. First one is the space vector modulation. First, I want to introduce you to the space vector modulation. Traditional pulse width modulation is widely used in motor control, but space vector modulation offers a significant improvement. So, how this SVPW space vector modulation different from the conventional PWM technique? In simple terms, space vector modulation fully utilizes the available DC bus, which results in higher efficiency. By incorporating a more optimal switching sequence, space vector modulation reduces the harmonic distortion in the inverter output. This reduction in the harmonic distortion leads to a smoother operation of motor with less noise and vibration. In space vector modulation, we represent the three-phase voltage vectors as a single rotating vector in a two-dimensional plane. This approach allows us to generate the desired output voltages by controlling the magnitude and angle of the vector. The result is a more efficient use of DC bus, giving us full range of voltage that inverter can provide. This translates directly into smoother and more efficient operation. This method is particularly beneficial in applications where efficiency and precision are critical, such as electric vehicles or industrial automation. Next, coming to the field weakening control. Permanent magnet synchronous motors typically operate within a certain speed range, and beyond this speed range the back EMF becomes too high, making it difficult to apply more voltage and increase the speed further. Field weakening control addresses this limitation by reducing the magnetic field in motor, allowing the motor to operate at higher speeds. In vector control, we adjust the D-axis current to reduce the magnetic flux produced by rotor magnets. This reduction in flux effectively weakens the magnetic field, hence the term field weakening. By doing so, we can maintain control over motor even as back EMF increases, allowing the motor to operate beyond its base speed. However, it is important to note that while field weakening extends the speed range, it does come with some trade-off. The torque capability of motor is reduced during field weakening, so it is crucial to balance the need for higher speeds with available torque. Field weakening control is particularly useful in applications where motor needs to operate over wide speed range, such as electric vehicles. Both low speed torque for acceleration and high speed operation for cruising are essential. Next, coming to the control strategies beyond the vector control, we have here direct torque control, an advanced method that directly controls the torque and flux of permanent magnet synchronous motor without the need of coordinate transforms. It offers faster dynamic response compared to the vector control. Now, if you see the working principle of direct torque control, in direct torque control, the torque and flux are directly estimated from the stator voltages and currents. The control system uses a lookup table to select the optimal voltage vector that brings the torque and flux to their reference values. Unlike vector control, which relies on proportional integral controllers and requires tuning, the direct torque control operates by directly manipulating the inverter switching states, results in faster response time. Next one is the sensorless control. Another technique that estimates rotor position and speed without physical sensors, reducing the cost and complexity, is sensorless control. This is specially useful in applications where sensors are impractical. Common methods includes back EMF estimation, high frequency signal injection and model based estimation. The model predictive control is also advanced control strategy that uses a mathematical model of permanent magnet synchronous motor to predict its future behavior. By optimizing a cost function over a finite time horizon, model predictive control determines the control actions that minimize errors and achieve the desired motor performance. Dynamic performance and constraints handling is a feature in model predictive control. MPC excels in handling multivariable control problems and system constraints such as current, voltage and torque limits. This makes it ideal for controlling permanent magnet synchronous machines in applications that demand high dynamic performance and precise control such as electric vehicles and robotics. Next, coming to the optimization based control, at each control step MPC solves an optimization problem to find the optimal control inputs that will minimize the deviation from the desired torque speed while respecting the system constraints. This optimization is usually carried out in real time requiring significant computational power. With this, I will conclude our lecture on PMSM. So, to summarize this today's lecture, first we started with the basics of PMSM like construction, next working of the PMSM machines. Thereafter, we have seen the DQ voltages of the permanent magnet synchronous machine, the torque expression of permanent magnet synchronous motor, and after that the torque speed characteristics, and at the last you have seen the control techniques like vector control, direct torque control and model predictive control. So, with this I will conclude our today's lecture. Thank you.